Stanford University.
What I wanted to do first was to show you the power of Lagrangians for solving simple systems, for solving simple problems. I think I'll show you two of them, two examples. They're similar to each other. I recommended last time that people study the double pendulum, and somebody, I think it was Sanjay, said, why not was it you who said, somebody said, take a wedge moving on a frictionless plane with another block of material sliding up and down. Who said that? Yeah, okay, Leonard said that. Yeah, they're both interesting, very similar problems, in fact. They're not hard problems. You could solve them both using F equals ma. It's a little tricky, and you'd probably spend more than a little bit of time figuring out the double pendulum for sure. That one would probably drive you crazy before you figured out how to use F equals ma to solve it. The blocks sliding around, a little bit easier. But if you know the rules of Lagrangian mechanics, it's a mechanical exercise. A completely mechanical exercise, you can be dumb as hell and still solve the problem. Sort of. Incidentally, by solving the problem, the first problem is to find a good pen. Okay, solving the problem does not mean necessarily solving the equations of motion. It means finding the equations of motion. Once you find the equations of motion, you can put them onto a computer and numerically solve them. They're just differential equations. So I regard a mechanical problem as solved when the equations of motion have been written down, for the purposes now. Now, often you want to do better than that, and of course you want to do better than that, but that can often be hard enough. So let's begin with the simple problem of a inclined wedge, or whatever we call it, sliding on a frictionless plane. It's sliding on a frictionless plane, and it has another object over here sliding up and down it, which for our purposes I'll just take to be essentially a point particle sliding up and down the plane. The point particle has mass little m, the wedge has mass big M, and you can set it in motion. And of course, the rule, of course, is that the little particle here is constrained, either mechanically constrained by some device, some sliders and other things, but it's constrained to move along the hypotenuse of the wedge. Okay? Find the motion. Find the motion of the system, and of course the motion means the motion of both things simultaneously. But as I said, what I mean is the equations of motion. All right, so the first step is always to assign a set of coordinates. You can think of them as generalized coordinates, but sometimes it pays to just use Cartesian coordinates. Sometimes it pays to use Cartesian coordinates. We could either call them x's or q's, it doesn't matter, but find a set of coordinates which are sufficient to describe the motion of the system. A set of coordinates. Coordinates don't mean the motion, coordinates mean an instantaneous configuration. So we want an instantaneous configuration of this system to be labeled by how many coordinates does it take to describe it? First question. All right, the assumption, let me state the assumption. The assumption is that the wedge is constrained to move along the frictionless surface here. Okay? It may do it by itself, meaning to say it may be heavy enough to stay on the surface, but if not, we will constrain it by means of the mechanical devices to slide only along the surface without friction. And we also constrain the small mass to move along the hypotenuse here. Then how many degrees of freedom? How many coordinates does it take to describe this? Yes, you're right, 2 is correct. 2 is correct. And for example, I could give you the x, let the horizontal axis be x. I could give you the x value of the corner over here, the x horizontal coordinate of the corner, that would locate the triangle for you. And then I could also give you either the x component of this mass or the distance along the hypotenuse. Let's use the x coordinate. One thing is true. In general, the choice of such coordinates is by no means unique. You just have to pick two of them and stick with them. All right, so I will choose for this example not the distance along the hypotenuse, just to make some variation. I will choose the horizontal coordinate. So this one, let's call this one big X, which I'll, just to make sure we don't confuse it with little x, I'll indicate it like that. That's the position of the corner of the triangle along the horizontal axis. And then the position of the mass here relative to the corner. Relative to the corner, not relative to the x-axis, but relative to the corner, I will choose another coordinate, little x. Now, I could also have just used the x position of this. Nothing wrong with that. In other words, not the x position relative to the corner here, but just the x position relative to the zero, to the origin of coordinates. Both will work. You get your choice, but I decide I am going to choose the two generalized coordinates, be the x position of this point and the little x position of the mass relative to the corner here. In other words, it's this distance over here. All right, so that's the first step. Choose some coordinates, make sure that they're good coordinates, make sure that they're not redundant. In other words, make sure that they are really sufficient to encode the instantaneous state of the system. First step. Next step, write down the Lagrangian. The Lagrangian is T minus V. Okay? Next step is T minus V. And so our next problem is to find the kinetic energy of the whole system. The kinetic energy consists of the kinetic energy of the moving block, the moving wedge, and also the kinetic energy of, let's call this guy over here the particle. Let's call it the particle. All right, this is easy to do. The kinetic energy of the wedge, what is that? That's just 1/2 its mass times its horizontal velocity squared, and its horizontal velocity is going to be capital X dot squared. That's the kinetic energy of the block. Next, we want to compute the kinetic energy of the small mass here, and here's where we have to be careful. It's not 1/2 m little x squared, x dot squared. It's actually 1/2 mass times the actual full velocity of this, and the full velocity of the particle has two components. One is the rate at which little x is changing, but that has to be added to the velocity of the block. The velocity of little m, let's write it. The velocity, let's call it the velocity of little m, is equal to, first of all, the velocity of the block to the right. That's capital X dot, plus the velocity, the x component of, this is the x component, incidentally. This is the velocity of the mass, little m, but the x component of it, as opposed to the y component of it. Okay, so first of all, it has capital X dot, but then on top of that, it has little x dot. That's the velocity of, that's the x component. What about the y component of velocity of the block? That is, to some extent, let's write down the y component. V little m y. Well, we don't need an extra y coordinate to describe the particle here. The y motion is completely dictated by the little x motion here. Okay? In fact, we can write an equation that y over x is equal, there's an angle here. I didn't write the angle. What should we call the angle? Alpha? Alpha. Not theta, I don't want you to say it. Alpha. Okay, so that angle is called alpha, and it's a number. It's not something that's free to change. And so y over x is equal to tangent of alpha. For example, if for 45 degrees, then y and x would be equal to each other. All right, so we can write then that y is constrained to move with x, and it's equal to x tangent of alpha. You know, just to keep this a really clean example, let's actually take the example where alpha is 45 degrees. You can work out the case with a general angle. With 45 degrees, then y is actually equal to x. And what is the vertical velocity? The vertical velocity is just y dot. It does not have a component from capital X. Moving capital X causes no motion, no vertical motion of little m here. So the vertical motion of the particle is strictly y dot, which is equal to x dot, or tangent alpha x dot if I kept the angle around. Okay, so now we have the components of velocity of the particle, and we can write the kinetic energy of the particle. 1/2 m, little m, standing for the particle mass over here, over 2, and then the x component of velocity squared, that's capital X dot plus little x dot squared. That's the x component of mv squared, and then plus m over 2 y dot squared, which is just another x dot squared, little x dot squared. That's the kinetic energy. Now we can open it up and work it out if we like. Why not? This is m over 2. Let's leave it this way. Let's just leave it this way. There's no particular advantage to expanding it out. Okay. What else goes into the Lagrangian? Potential energy. What potential energy is there? Well, I'm assuming that there's no forces acting, explicit forces on the system acting in a horizontal direction. No gravitational force pulling it horizontally, but let's assume there's a gravitational force pulling it vertically. Then there would be the gravitational force acting on big M, but that's not important because big M can't move vertically. The potential energy of big M is fixed by the fact that it's always at sea level, whatever, or at the level of the motion here. So we don't need to write down any potential energy for big M, but we do need to write down a potential energy for little m because its altitude can change. In fact, its altitude is just x. So what's a good potential energy? A good potential energy would be V equals little mg times y, or equivalently x. So this is T, kinetic energy, sum of two terms, and then we want to subtract the potential energy, which is just minus, just subtracting it is just mg little x. And that's on Lagrangian. That's all there was to it. How do we work out the equations of motion? Euler-Lagrange equations. Euler-Lagrange equations. Okay. I don't particularly want to do that, but what I do want to do is work out what the conservation of momentum says. You can work out the equations of motion for this. Well, let's write down one or two things. How about P capital X? the momentum conjugate to capital X. Now you might think it's just mx dot. That would be the usual mechanical momentum of the thing, but it's not the definition of momentum we've been using. The definition of momentum, as we've defined it, is the derivative of the Lagrangian with respect to capital X dot. That's its definition. You got to stick with the definitions. The derivative of the Lagrangian with respect to capital X dot, derivative of the Lagrangian with respect to capital X dot is px, and what is it? It is m over capital M x dot the thing, of course, that we expect, but then there's more to it from here. From here, there's plus m over 2. Well, the 2 is going to cancel, and there's little m times the derivative of this thing here with respect to x dot, and that's another factor of capital X dot plus little x dot. Everybody see what I did? I differentiated what was in here with respect to capital X dot, and that just gives me capital X dot plus little x dot. That's the definition of the momentum conjugate to x. What about the momentum conjugate to little x? P sub little x is equal to the derivative of the Lagrangian with respect to little x dot. What did I do here? Did I? Yeah, okay, right. What is that? Everybody remember where this term came from? It was the y motion. I had forgotten for a second. I was looking at where did that one come from? Yeah, that was the y motion. Okay, so notice the y motion actually makes a contribution to the x component of canonical momentum. We'll call it canonical, that's the word for it, canonical, or momentum conjugate to little x. What is it? It's m over 2, big x dot plus little x dot. Sorry, not m over 2, but just m, big M. No, little m from here, and then another one from here, plus another little m times little x dot. Now, this may surprise you. You might have thought that momentum is just good old momentum, mv. That is not the definition of momentum that we use in the abstract mathematical system that's called classical mechanics. So this is it. These are the definitions of momentum. Is there any conserved momentum? Well, is there any symmetry? Is there any symmetry that the system has? The answer is yes, it does have a symmetry. It has a translation symmetry. But when you translate, what do you have to do with little x? Well, first of all, what happens when you translate the whole system? What happens to big X? You add a little constant to it, right? You add an epsilon or a delta to it. What happens? That's big X. What happens to little x? Nothing. If you translate the whole thing and really translate it, little m moves with big M. So little x doesn't change when you translate. Okay, so let's write down the symmetry. The symmetry is delta big X. We used to use delta, but we wound up saying that epsilon was a better symbol for it. Just call it epsilon, a little number. What about little x? 0. Okay. Now let's work out the conserved quantity. There is a conserved quantity. We can be sure there's a conserved quantity just because it has a symmetry. And that conserved quantity, Q, is equal to the sum over all the coordinates of the corresponding momentum times the little change in the corresponding coordinate. What is the f function for this here? The f function, remember the delta of the coordinates is equal to f times epsilon? F is 1. What is the f function here? 0. Okay, so p times the corresponding f function. For capital X, f is 1. For little x, it's 0. So there's only one term, and it's just p capital X. In other words, as you might have expected, the x component of momentum is conserved. That's the conserved quantity. But it's not the mass times the velocity of the block here. That's not conserved. Why isn't it conserved? The reason it's not conserved is that because there are forces between big M and little m. Well, you know, if you try to give big M a push, then there's a force exerted on little m exerts a back force on big M, and there are forces on big M. So the momentum, the ordinary momentum, the conventional momentum, namely mv, of this block is not conserved. What is conserved is the canonical momentum conjugate. Oh, how do I know it's conserved? Yeah, how do I know it's conserved? I know it's conserved because there's a symmetry. But we can look at the equation of motion. We can look at the equation of motion and say the equation of motion is that px dot, let's write it down. Let's get rid of this. Px dot is equal to what? Derivative of the Lagrangian with respect to capital X. There is no capital X in the Lagrangian. There's only capital X dot. Capital X itself does not appear in the Lagrangian. It's a cyclic variable. It's a cyclic variable which simply doesn't appear in the Lagrangian, and so this is equal to 0. That's the conservation of momentum for this system. And if you want to know what it really is, it's capital M, capital X dot, plus little m, little x dot, as you might have expected. It's really the total momentum. You can work that out. Yeah, it's true. It's just the ordinary total momentum. But it appears in this problem as the momentum conjugate to capital X. All right, we can work out all of the equations of motion. How about the vertical? How about the, is there a symmetry with respect to vertical motion? No. No. If you move, the triangle is not allowed to move up and down. And this thing only moves up and down when the triangle moves, but when it does move, the potential energy changes. So there's no corresponding component of y momentum that's conserved. So this was an easy one. Let's see, did we write down the equations of motion? Well, here's one equation of motion. Let's write down the other one. That was d by dt of p sub capital X, and that was equal to 0, because in the Lagrangian here, there just is no dependence on capital X, no explicit dependence on capital X. What about p sub little x dot? That's equal to the derivative of the Lagrangian with respect to little x. Does little x appear? Yeah, little x appears right over here. Okay, so that's equal to minus the derivative of the Lagrangian with respect to little x, which I believe is plus, is it plus? Yeah, the derivative of the Lagrangian with respect to, minus the derivative, yeah, it's equal to mgx.
No x, right?
Just mg, thank you. Just mg. So it's a little bit surprising that p sub x dot, even though x is a horizontal coordinate, nevertheless, there is a gravitational field associated with it. And of course, the reason is because x is equal to y. Because x equals y, There's a potential energy when you move little x, and that manifests itself as a right-hand side to the equation here.
Should that be negative or positive?
Positive, I think. Px dot is equal to plus. And the reason, let's see, am I right?
It's plus dl dx, but dl dx itself has a negative sign.
Let's see.
It depends on the direction of x.
The L by the x has a minus sign, but we're supposed to put minus dl by dx on the right-hand side here. No, we're supposed to put plus dl by dx. Excuse me, minus. My mistake.
We have the minus over in the Lagrangian because it's t minus v, correct?
Yeah.
Okay.
Right, that's right. So the equations are dl by dx is equal to dv, not minus dv by dx. Wait. Yeah. Yes. Okay, that's an example where it wouldn't be terribly hard to write down the Newton equations, F equals ma for the block and for the particles separately, but you'd also have to remember that there are forces between them, and you'd have to worry about the forces between them. They're equal and opposite and so forth. You'd have to solve for the forces between them. In this context, we never had to talk about the forces between them. It just didn't enter into the discussion. The forces between them are simply assumed to be such that the constraint is satisfied, namely that the particle stays on the inclined plane. So it's much easier. All right, I'll show you the other example. You can work this one out yourself. It's a bit more tedious. The example is the double pendulum, very similar in many ways. The double pendulum this is just a vertical axis. Pendulum is suspended from a point up here. Let's take the case where the pendulum length is 1 so that we don't have to keep track of a bunch of irrelevant stuff. And let's take the pendulum bob over here to have unit mass, so again we don't have to keep track. This is a simple system, but now we add to it a second pendulum connected to the first pendulum. Like that. So they're both free to swing. The length of each rod here, of each pendulum rod, is 1. And for simplicity, let's take the mass of each bob, the pendulum bob, this one and this one, to both also be 1. All right, so how do we describe this system? What first, again, rules. First thing, find a set of good coordinates for it. Well, it's pretty clear the good coordinates are angles. No, you don't, when I say the good coordinates, you're perfectly free to choose other coordinates. But, you know, I have some instinct here that this is an angular problem. And so I guess it's not completely mechanical. The choice of coordinates, to some extent, you want to choose coordinates that make the problem easiest. That can be an art. But you know, if you choose wrong coordinates or impractical coordinates, it just means your equations will get long and ugly. It doesn't mean that you'll be doing anything wrong. All right, so we really have two choices here. The angle here, I can't think of any possible reason why I would not use the angle of the first pendulum relative to the horizontal as a coordinate. The ambiguity, and it's not an ambiguity in the problem, again, it's an ambiguity in how you decide to solve the problem, concerns the second pendulum. Do you want to choose the angle relative to the vertical and call it something, or do you want to choose it relative to the line that would be the extension of the first one and call it alpha? Let's use the black chalk. All right, so either phi, which would be relative to the vertical, or alpha, which is relative to theta, so to speak. All right, so we could take a vote. But I'm not going to take a vote because I happen to know the one which gives the easier answer. The easier answer is to choose alpha like this, relative to this one. Now let me tell you why, before we do anything else. Let's forget for the moment the gravitational field. Let's forget it. This is just a thing swinging around. If it were just a single pendulum, there would be no gravitational field, and it would just swing around and around and around and around. Let's take the single one first of all. There's an obvious symmetry. The obvious symmetry is just angular symmetry. If there's no gravitational field, then there's an obvious symmetry, just rotation. Well, this system also has a rotation symmetry. If you rotate the entire, just keeping this angle fixed, keeping this angle over here fixed, rotate the entire thing, that's also a symmetry if there is no gravitational field. And that would be true no matter how you choose to coordinatize it. But an advantage will be that the symmetry operation will only involve theta and not alpha if we choose alpha to be relative to theta. If we chose alpha to be relative to the vertical, whoops, then when we rotate the whole system, both theta and alpha both transform. And it makes it a little more complicated, but nothing that we couldn't handle. Nevertheless, we'll use alpha. Okay, so how do you figure out the kinetic energy? Well, you could try working directly with the angular variables, but it's often a little more intuitive to say, look, let's work out the kinetic energy by starting with the kinetic energy in Cartesian coordinates and then rewrite it in terms of the angles. So it's often a good thing to realize that your objects are moving around in Cartesian space and that the kinetic energy is just 1/2 mv squared. All right, so what you do is you say, all right, let's just for the moment, as an auxiliary step here, let's introduce the x component and the y component of this pendulum bob here. Notice I'm measuring y vertically downward. Doesn't matter, but just for variety, we'll measure y downward. So this is a positive y over here. Okay, so what is the relationship between x, y, and theta? Well, first of all, x is equal to sine theta. Y is equal to cosine theta. So x and y are not new variables. They're just sine theta and cosine theta, that's all. However, we can also write the velocity of this pendulum bob. X dot is equal to theta dot times cosine theta, and y dot is equal to theta dot minus theta dot times sine theta. We just differentiated with respect to time, found x dot and found y dot. Here are our components of velocity. We really don't need x and y anymore. Here are our components of velocity. But now we also need to know the components of the velocity of this guy over here, also a unit rod here. And to do that, we have to figure out what the x and y components of this guy are over here. What should we call them? Herman.
Last time it was Herman.
Herman? Okay, Herman. But I need a symbol for Herman. It's not a question of what his name is, it's a question of what symbol do we use for Herman. Let's call it x prime and y prime. X prime and y prime. Okay, so what are x prime and y prime? All right. Here, it is convenient to think of the angle relative to the vertical. The angle relative to the vertical is alpha plus theta. Okay, good. What is x prime? X prime, let's write it here, x prime is going to equal x plus sine of theta plus alpha. Is that clear? sine of theta plus sine theta plus alpha. That's just this bit of it over here. So I added this bit to this bit. But x I already know. It's sine of theta. So x prime is sine of theta plus sine of theta plus alpha. What about y prime? Y prime is going to equal y, which is cosine theta, plus this bit over here, which is just going to be cosine of theta plus alpha. What about the velocity of this one here? We just differentiate with respect to time, and we find that x prime dot is equal to x dot, which is theta dot cosine theta, plus the time derivative of this. Sorry, did I? Theta. Theta, thank you. Plus the time derivative of this, which is plus theta dot plus alpha dot times cosine of theta plus alpha.
Minus that, right? Minus cosine, right?
1 minus cosine. Derivative of sine is cosine, yeah, right. We also have y dot squared, y prime dot squared. I'm not going to write it. It does involve some minus signs and so forth. What do we do with this? We write down the kinetic energy of the two objects. One of the kinetic energies is just x dot squared plus y dot squared. That's just theta dot squared. Why? Because cosine squared plus sine squared is 1. So there's one term which is theta dot squared, but there's also x prime dot squared and y prime dot squared. And it's a bit of a mess. It's not too bad. You spend a few minutes, probably of order 60 seconds. I can probably do it in 45 seconds. You can probably do it in 60 seconds. I'll write it down for you just to show you the type of thing that you get. All right? This is the kinetic energy. T, kinetic energy, is equal to theta dot squared plus theta dot plus alpha dot squared over 2 plus theta dot times theta dot minus alpha dot times cosine of alpha. Okay. What about the potential energy? Yeah.
Sorry, I missed that. Is that the kinetic energy obtained by adding together the two?
Yeah. X dot squared plus y dot squared plus x prime dot squared plus y prime dot squared over a half. There's no, I didn't make a mistake. There is no missing half here. There were two terms, and I combined them together. This is the kinetic energy. Let's, for the moment, forget potential energy. Let's not think of this as a pendulum for a minute. And look at this. Is there a conserved quantity? Well, it better be a conserved quantity, because if there is no gravitational field, then there's a rotation symmetry. And the way to see it is that there's a cyclic coordinate here. Which is the cyclic coordinate? It's the one that doesn't appear in the Lagrangian. It's theta. Theta doesn't appear in the Lagrangian, and that means alpha does. Alpha does. Here's cosine alpha. But theta itself doesn't. By theta appearing, I mean without a time derivative. Theta without a time derivative doesn't appear. And so you can be sure that whatever piece of theta is, its time derivative is going to be 0. Let's not work it out. You can work it out yourself. You just differentiate the Lagrangian with respect to theta dot, and you'll find a conserved quantity. The conserved quantity really is just the sum of the angular momenta of the two bobs, or the two pendulum bobs. But you don't even need to know how to calculate the angular momentum. You just say, look at this thing. There was a symmetry. In this particular case, it was just the fact that there was a cyclic coordinate and a corresponding conserved quantity. Had you used the other coordinate, namely the one relative to the vertical, neither coordinate would be cyclic, but you still would have found a conserved quantity if you went through the rules. Okay, so, and it would be the same conserved quantity. All right, so those are just two examples. And believe me, if you wanted to do the double pendulum here by F equals ma, that would be a little bit nasty. But here we got it. Once you get the Lagrangian, you got the equations of motion, you have the conservation law. There is one, oh, we left out one thing. Yeah, we did leave out the gravitational force. Now that would violate the rotational symmetry, and you wouldn't have a conservation law. But let's just write down what it would be. What's the potential energy? The potential energy is mg times the y coordinate, it's actually times minus the y coordinate. And the minus the y coordinate involves cosine theta. So the potential energy, this would be the potential energy, and we would subtract it. So T minus V would be, did I do this right? No. No, I did not do it right. No. That's only the first mass. And incidentally, since the mass is 1, it's just g cosine theta. That's only the first, that's the potential energy of this one. And the potential energy of the other one would be minus mg cosine, I guess it's cosine of alpha plus theta. Just the height of this one.
No, it's cosine theta plus cosine alpha plus theta, right?
You're right. Cosine theta, yeah. Whatever it is, it's the height, which is the sum of these two. You're right, it's the sum of two cosines, and you write it out. And there's some potential energy here that you can write down. Once you've written the potential energy and the kinetic energy, to find the equations of motion, you just mechanically work out Lagrange equations of motion. So in that sense, the Lagrangian is a very compact, easy way to take a complicated system, which in this case, has rods. It has all kinds of things going on. The rods, when the rods try to stretch, they exert forces. All sorts of complicated things go on that you'd have to take into account in F equals ma, and it's automatically taken into account. So that's the power of the Lagrangian formulation of mechanics. Yeah.
Expression for T minus V there, should that dot minus alpha dot be theta dot plus alpha dot?
Very likely. Maybe. I don't know. Yeah. I think so. You're right. Yeah, I think that's right. Well, one of the two of these is wrong, I'm sure. Let's see, which one?
When you take the x dot prime and square that, you have right behind you, you get a theta dot term.
This I think should be minus, and this I think should be minus. That's what I have in my notes anyway. But my notes could conceivably be wrong.
Depends on which direction's positive for alpha.
Right, it does. And we're not going to worry about it. You get the point. You can fiddle with it yourselves. This thing can be solved. The two combined equations. There's another concern. What's the other? Even with the gravitational field, but especially without the gravitational field, it's not hard to solve. Even with the gravitational field, it's not hard. To solve it, you need to use two conservation laws. What's the other conservation law? Energy, T plus V. If you write down that T plus V is fixed and call it energy, and the angular momentum you call just a fixed number L, you'll find out that you have enough equations to completely solve the entire system. And it's fun. You have to do an integral. When I say solve it, you have to do an integral, but just an ordinary integral. Okay, the thing swings around, does complicated motion. It's a fun system to work out. It's probably even more fun to watch, to program it on a computer and watch it move, and it moves in chaotic, interesting motions.
Is there a way that you can see that it's chaotic from looking at the equations?
No, not really. And in fact, sometimes there are systems which have transitions as you change parameters. They can go from not chaotic to chaotic. So no, there's usually no easy way. Yeah. And if you don't know what chaotic is, don't worry, we'll come back to it.
For conserved systems, P dot has got always have to equal
Say it again.
0. For conserved systems, P dot always has to equal 0.
P dot always equals 0?
Yeah?
No, P dot is equal to dv by d, is equal to the derivative of Lagrangian with respect to theta, which in many cases is just the derivative of the potential energy with respect to theta. It's only equal to 0 here because the Lagrangian doesn't involve theta. It's a cyclic coordinate.
Okay.
Yeah.
The momentum conjugate to a cyclic.
Yeah. The momentum conjugate to a cyclic coordinate is always conserved. And that's a special case of the symmetry idea. It's a special case where the symmetry acts on only one coordinate. All the others are left fixed by the symmetry. So for example, here, the symmetry operation acts on theta, but keeps alpha unchanged. So when the symmetry is defined, or when you define your coordinates in a clever way, so that only one of them shifts under the symmetry operation, that's when you have a cyclic coordinate. But as I said, you don't have to be clever in your choice of coordinates. If your goal is to write down the equations of motion and stick them on a computer, and you don't care how complicated they are, any set of coordinates will work. Yeah.
Pardon my ignorance here, but suppose that we just have a single pendulum and no gravitational force.
Okay.
Then we give it any kind of motion, it's just going to go around and around,
Right.
right? And it,
That's conservation of angular momentum.
right. And if we have a double pendulum, then if both of them start out with no motion, it's just going to sit there, right? But if we give them each an initial velocity, then
Yeah, it does. That's correct. That's correct. And it can do extremely complicated things, and still the angular momentum is conserved. Okay, so yeah.
Without gravity, though, the theta dot and alpha dot are constant, right?
No.
Oh, theta dot. So the angular velocity of each.
No, I don't think so. Let's see. No, I don't think so. Let's work out. Okay, let's work out the equations of motion. Let's work out the equations of motion and see. Okay. To say that theta dot is constant is to say that theta double dot is 0. Right?
That's really just a question because so it's.
Well, that's the definition of what theta. Right. All right. So let's check. Let's work out the equations of motion. Partial of L with respect to theta dot. We're first going to work out p sub theta. So that's theta dot from here, twice theta dot from here, dl by d theta dot. What about from here? There it'll give us plus theta dot minus alpha dot from here. And then from here, another twice theta dot. And then minus alpha dot. Does that look right? That's cosine alpha. Let's see. This times cosine alpha, right? And what does that equal? That equals dl by d theta, which is 0. Or another, no. This is, what is this? This is p sub theta, dl by d theta dot. Okay? Now we want to time differentiate it. We want to take d by dt of this and set it equal to dl by d theta. All right, so let's take the time derivative of this. The time derivative of this has theta double dot, alpha double dot. Now, it has two terms from here. One of them is to differentiate the thing inside the bracket. The other is to differentiate the cosine alpha. So there will be one term which will be theta double dot cosine alpha, the alpha double dot, and then there will be twice theta dot minus alpha dot times another alpha dot with a minus sign times sine of alpha, coming from differentiating the cosine alpha. And that is the thing which is equal to 0.
Two.
Two?
To the derivative of, with respect to theta. The derivative Lagrangian with respect to theta. This is the first term in Euler-Lagrange. The second term is the derivative of the Lagrangian with respect to theta.
Say it again?
Which is zero. The last one.
0. The LD theta is 0. There's no theta in here.
Oh, okay, good.
Right. Right. Yeah, this is in the absence of a gravitational field. Good. Yeah, so this is just 0. All right, this is the thing which is 0. Not theta double dot, not necessarily alpha double dot. And in fact, what's going on is they're exerting torques on each other. Their motion, their relative motion and the swinging is exerting torques on each other. And the effect is that, theta double dot is not equal to 0, alpha double dot is not equal to 0. We could write out the other equation also, the equation for alpha. You know how to do it. But no, the answer is no. The angular velocities of the individual bobs will not be conserved. It's the angular momentum that's conserved. And they transfer angular momentum back and forth between them. You know what it's like? Supposing you just have two particles on a spring. The two particles move off. Momentum is conserved. Do the individual accelerations, are the individual accelerations 0? No, they go like this. They exchange momentum back and forth, and neither velocity is constant. It's true the center of mass velocity is constant. Well, there's an analog of the center of mass motion for the rotations, but it's not this angle, it's not this angle, it's some combination of the two of them. So there is some kind of notion of a center of it's actually center of moment of inertia. But it's neither alpha dot nor theta dot. They just transfer energy and momentum back and forth between them.
In this case, the forces are going through the rods, right?
The forces are going through the rods, yeah. Right. But if you look at this one over here, there's a force on this particle going this way, and there's a force on this one going this way, or something like that. There is a net torque on this. All right, so that means there would be a net force in this direction over here, something like that. And that force is a torque on this angular direction here, and it causes an acceleration of theta. If you don't know what a torque is, it doesn't matter. It's just a force which tends to rotate things. Okay, now we want to come to the Hamiltonian. The Hamiltonian is energy, and that, of course, is one of the very great significances of the Hamiltonian. It is energy, and it's conserved. But the Hamiltonian is the basis of another distinct and new formulation of mechanics. We have three formulations. The first, so far, the first is Newton's equations. The next is the principle of least action, which is the same as the Euler-Lagrange or Lagrangian formulation. And the third, did I say there were three already? Yeah. I only count two. Am I right? The third formulation is the Hamiltonian formulation. And it looks different than either of them. It's equivalent, but it looks different than either of them. And it also, in its own way, has enormous power. I'm sort of tempted at this point to go back to something in the very first lecture and tell you to keep your eyes open for something like this happening in Hamiltonian mechanics. Remember we discussed various laws of dynamics for simple systems. We had one like that. We had a six-sided die, which we had various kinds of laws that we made up. And we said these are good laws. But we also talked about bad laws. Bad laws, for example, would be this. This law is deterministic. It tells you where to go next, no matter where you are. But it fails to be able to tell you where you were in the past. If you find yourself at this point, you could have come from here, or you could have come from here. These are bad laws. I told you in the beginning that the analog of these bad laws are forbidden in physics. The easiest way to see that they're forbidden, or the analog idea, is from Hamiltonian physics, from the Hamiltonian. We're going to find that the Hamiltonian, that an analog of the same thing will be forbidden in Hamiltonian physics. Now, what characterizes this? Here's another example. Let me draw another example. A node at the center, several states around it, and here's a law, possible law, or an impossible law. If you're here, you go here. If you're here, you go here. If you're here, you go here. And in fact, no matter where you are, you wind up here. And then where do you stay after that? You just stay there. Deterministic as hell, but not reversible. Not reversible. Notice that in these laws, there is often a sense of convergence, a sense of convergence that there are more arrows pointing in to a point than there are arrows going out. That's the kind of forbidden thing. And of course, the opposite is also forbidden, namely a divergence where arrows come out of a point. And well, I suppose we can have this one go around to itself again. This time, we can't even say what the future is. This time we can say what the past is, but we can't say what the future is. If we're over here, we don't know where to go next. Do we go here? Do we go here? Do we go here? And so forth. Neither a divergence nor a convergence is allowed if our laws of physics are intended to be reversible. Yeah?
Just a question. The top right-hand diagram is forbidden one?
This one? Yeah, yeah. Mm-hmm.
Now, if you put that in a gravitational field.
Put what in a gravitational field? Hmm?
And you've got the loop at the bottom and the point at the top.
You're reading too much into this. These are just three abstract states.
You spin a rope trick, and they just change places.
Hmm? Okay. But you're reading too much into it.
So it's cyclical.
This law of physics is not cyclical. If you start here, you go there, and then you go here, 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 here. It's cyclical after a certain point, but it never cycles back to here.
So how do you differentiate the bottom forbidden state from, let's say, something like a black hole?
Right. With difficulty. With difficulty and subtlety. Right. Let's not, it's a fair question, but I won't answer it. Okay. Keep in your head the idea that the flow associated with a law of physics should not have a divergence or a convergence. Keep that in your head. That's the meaning, the ultimate meaning of reversibility. Even at this point, I haven't told you what convergence and divergence mean, except in this context. Okay. let's define or prove or work out, derive Hamilton's equations of motion. Now, in Hamilton's equations of motion, the focus is not on the q's and the q dots. It's on the q's and the p's. What are the p's? The p's are the momentum conjugate to the q's. The number of things that you need to know to get a mechanical system started are twice the number of degrees of freedom, twice the number of q's. It could be the q's and the q dots, or it could be the q's and the p's. In fact, in general, for good mechanical systems, the q dots can be solved for in terms of the q's and the p's. I'm going to give you some examples to show you how this works. So that the q dots can always be thought of as functions of q's and p's, and you forget them and you think about the q's and the p's. I'm going to show you how this works. This may be a little bit obscure right now, but I'll show you how it works. The focus is on the q's and the p's. And we're going to find that there's a symmetry between the q's and the p's. Not the kind of symmetry we've talked about up till now, but a kind of equality between them. That does not mean that p is equal to q. It means they're sort of on the same footing in the Hamiltonian formulation. In the Lagrangian formulation, the p's were just these wacky things where you differentiate the Lagrangian with respect to the q dots. In the Hamiltonian formulation, it's the p's and the q's and the Hamiltonian. And the Hamiltonian is thought of as a function of the p's and q's. No q dots ever appear. Well, q dots appear, but not in the formulation of the Hamiltonian. Okay, so let's start with an example. Let's do an example. I think it's best to start with an example. Let me remind you what the Hamiltonian is. The Hamiltonian is equal to the sum over all the coordinates of q dot times p. I won't bother putting the little i's in. Sum over all the coordinates minus the Lagrangian. We worked that out last time, and we found out that as a consequence of the Euler-Lagrange equations, this quantity is conserved. I'm not going to do it again. This quantity is conserved. It's the conserved energy, and it's the Hamiltonian. Okay. Now I want you to think in the back of your mind that q dot can always be re-expressed in terms of the q's and p's. So think of this Hamiltonian not as a function of q dot p and q, but think of it as just a function of p and q. Let's work out an example to see how this works. The example is the good old harmonic oscillator. I'm going to take the harmonic oscillator with a Lagrangian, t minus v. Here's the Lagrangian. Now, why am I writing it this way? I'm writing it this way because it's the simplest way to write the Lagrangian for harmonic oscillator. What is the parameter? What is the important parameter about the harmonic oscillator which comes in as a numerical parameter into the oscillator? Omega. Omega. You might say m and k, meaning the mass and the spring constant, but in fact, by a suitable change of variables and a rescaling of the coordinate, you can get rid of m and k and replace it by just omega. I'm going to assume that's done, and it doesn't matter how it's done. You can just take this as a Lagrangian, as a sample Lagrangian. 1 over twice omega times q dot squared minus omega over 2 q squared. This is kinetic energy. And either because I just like putting a 1 over 2 omega there, or because you can always do it, you can always rearrange the harmonic oscillator to look like this. Notice the omega goes in the denominator here and the numerator here. This is kinetic energy This is potential energy. This is a restoring force. This is potential energy. And omega is just a parameter. Okay, let's work out the various things that appear on the left-hand side, in this Hamiltonian side. First of all is P. What is P? P is the derivative of the Lagrangian with respect to the velocity, and that's just equal to q dot over omega, right? Q dot over omega is P, but instead of reading this P is equal to q dot over omega, I'm going to read it the other way. Q dot is omega times P. In other words, I'm going to read this as telling me what q dot is in terms of P instead of P in terms of q dot. I haven't done anything very brilliant. I've just expressed q dot in terms of P. And now we're going to rewrite the Hamiltonian. All right, so the Hamiltonian then, here it is, h of q and p, is equal. There's only one coordinate in this case. There's no sum. Q dot times p. But q dot is omega times p. So what do I get? I get omega p squared. Omega p squared. Now we have to subtract the Lagrangian. So we have to subtract, I'm going to do it in two pieces, 1 over 2 omega. And what is q dot squared? Q dot squared is omega squared p squared. Okay, so let's write it. Minus 1 over 2 omega. P squared, omega squared. Oh, that's nice. The omega in the denominator is canceled by one of the omegas in the numerator. Keep in mind, but I want to write down the last term. The last term in minus L is plus omega over 2 q squared. Okay, so notice what happened here. The q dot p term combines with the kinetic term in the Lagrangian. Here's the kinetic term in the Lagrangian. It's being subtracted off. It's not omega squared p squared. It's a half omega squared p squared. Let's cancel out the omega here. This and this are the same except for the factor of 2. So what do I get? I get omega p squared over 2 plus omega q squared over 2. Q squared plus p squared. That's the Hamiltonian. And the important things that I want you to come away with is that when you're doing the Hamiltonian version of classical mechanics, you get rid of the q dots. You get rid of the q dots by solving for them. Now, sometimes you can't solve equations. Not because you're not powerful enough to solve the equations, but because the equations don't have solutions. You can write down Lagrangians for which there will not be solutions. They're bad systems. They're systems which cannot come from quantum mechanics. So unless it's possible to solve for the velocities in terms of the momenta, this is not considered a legitimate Lagrangian, even though there may be sensible Euler-Lagrange equations. All right, so that's the idea of a Hamiltonian. You write down q dot p minus L. It depends on q dots, but you get rid of the q dots by solving for them in terms of the p's. And now you have the Hamiltonian. Okay, let's think about this for a moment. This is kind of interesting. Omega over 2 times q squared plus p squared. Oh, if you think it was magic and a wonderful thing that the omega came out in the numerator in both terms here, I set it up that way. I did it on purpose. That's why I put the omega in the way that I did, so that in the Hamiltonian it would just come out as a factor. Okay? There was no magic there. It just was a trick that I did in the Lagrangian so that it would come out this way in the Hamiltonian. Okay, so the energy, the Hamiltonian is the energy. It's proportional, first of all, to omega, but to q squared plus p squared. One of the things we're going to learn to do is to draw diagrams of the motion. This is phase space, and phase space is the space of the q's and the p's. Q horizontally, p vertically. Now, of course, once we go beyond 1 degree of freedom, we won't be able to draw it on the blackboard. If we have 2 degrees of freedom, then we have 4 variables altogether. 3 degrees of freedom, 6 variables. But at least we can draw QP space for 1 degree of freedom, QP. Think of this function here. This function is constant with respect to time. Now, what are the surfaces or what are the trajectories of constant q squared plus p squared? They're circles. They're circles of different radius. Different radius means different values of q squared plus p squared, and therefore different values of energy. So here's what we've learned. We've learned that the system, the harmonic oscillator system, moves through phase space with time on circular trajectories. Oh, actually, I think they're going to, if I remember correctly, I think they go the other way, clockwise rather than counterclockwise. They move on the system moves on circular trajectories. Whatever the value of q squared plus p squared when you begin, it must stay that. That means it has to stay in a circle. Why must it stay that? Because we already know that, that this thing is the energy, and energy better be conserved. On the other hand, we should try to see what the equations of motion actually say, but in particular, what the equations of motion say in Hamiltonian form. So this is just an observation that with the notations that I've used here, the q's and the p's move on circles. Wherever you start the system, any place you start the system, it'll be on one of these circles, and then it will just move in a circle. I keep drawing counterclockwise. I think it's clockwise orbit, indefinitely, forever and ever. You know what this is like? We talked about conservation laws the first day. We talked about, for example, laws of physics like this. These are good laws. This is a good law of physics. This is a law of physics for the die. If you're on a cycle, if the laws of physics, if the laws of motion happen to divide the space up into separate cycles, then there's a conservation law. The conservation law simply corresponds to which cycle you're on. If you're on here, you never get off there. If you're on here, you never get off there. Well, it's a very similar situation. If you're on this trajectory, you stay there. You never get off it. If you're on this one, you never get off it. It's just energy conservation. There are other conservation laws, and therefore other surfaces in which you get trapped on. But this will do for the harmonic oscillator now. Okay, what I want to do in the remaining time tonight is to derive Hamilton's equations. And to show you how they work for the harmonic oscillator, and that will be enough for tonight. We use a standard trick of calculus. If we have a function of some variables, let's say q's and p's, and I make a little disturbance of the q's and p's, I move them a little bit in the phase space, the function changes. If the function is a non-trivial function, it changes. How much does it change? Not changing with time, just changing because we've moved the point a little bit in phase space. Just a functional dependence. What's the change in f? The change in f is given by the partial derivative of f with respect to q times delta q plus the partial derivative of f with respect to p delta p. This is just standard calculus of two variables. The change is the change in f because you changed q a little bit times a little change in q plus df by dp, little change in p. Okay, that's standard. You can read it the other way. You can say if somebody gave you that the change in f was proportional to something, let's just call it the thing over here. Let's not call it df by dq. Let's call it a. And let's call this one over here b. Somebody told you that the change in f is a times delta q plus b times delta p. You could read off that a must be the partial derivative of f with respect to q, and b must be the partial derivative of f with respect to p. So you can read it in two ways. One way is just to say, look, this is what we know from calculus. The other way is to say, look, if I give you delta f and it's got an a and a b, then a and b must be these derivatives. Okay, that's the trick. That's a central trick to so much of classical mechanics, or the derivations in classical mechanics. And we've used it before, but let's apply it to the Hamiltonian itself. Let's write the change in the Hamiltonian when I make a little change, whatever that change happens to be. Except now, I'm not going to tell you what the Hamiltonian is in terms of q and p. I'm just going to tell you that it's q dot p minus L. I'm going to go back to this equation over here, and I'm going to say, what's the change in the Hamiltonian if I change things a little bit? Whatever it is that I'm going to change. I'm going to change q dot p, everything, whatever it is that I change. All things. What's the change in h? Let's write it over here. Let's do it over here. Change in h. Well, first of all, there's a sum. There will be a q dot times delta p. There will be a change in q dot times p. The change in a product is the change in one factor times the other. Here's the change in p times q dot. And the change in the other factor times the first one. That's it. And then there's minus the change in the Lagrangian. Minus the change in the Lagrangian. And the change in the Lagrangian is the derivative of the Lagrangian with respect to q dot times the change in q dot minus the derivative of the Lagrangian with respect to q times the change in q. I'm writing it as if there were only one coordinate. You can put back all the summation signs, and the little sub i's. Oh, I actually put a summation sign here, didn't I? Yeah. I've changed everything that could be changed. Q dot, p, get this term, and in L we can also change q dot and q. There's nothing else to change, and this must be the change in the Hamiltonian. Okay, some things cancel. Fortunately, it looks kind of ugly, but some things change. Some things cancel.
What's the L by dq dot?
Ooh, the L by dq dot, thank you. Okay, what is the L by dq dot? P. This is P delta q dot. But here's P delta q dot. Magic. We get rid of it. I'll let you stare at it again before I get rid of it. The L by dq dot is P, and so these two things cancel. That's nice. All right, so we have q dot delta p, and here we have dl by dq. What is dl by dq?
It's the time derivative of the momentum.
P dot.
Yeah.
Right. So let's put that in. minus p dot times delta q. That's it. That's the whole change in the Hamiltonian. When I change q dots, p's, when I change everything in sight, the Hamiltonian changes by that much. Now keep in mind, at the end of the day, we're going to want to replace the q dots by some functions of p. We're going to, q dots are now, will be functions of p, but for the moment, here we are. Well, now let's compare that with this equation over here. The change in a function when you change q a little bit is df by dq. When you change p a little bit, it's df by dp. So now look what I can do. I can read off from here that the derivative of h with respect to p, that's the change in h when I change p a little bit, is the q velocity. And the other equation is that the derivative of the Hamiltonian with respect to q is minus p dot. And there's an equation like this for each I. That's it. That's the whole upshot of Hamilton's equations. These are Hamilton's equations. If you know the Hamiltonian as a function of q and p, then Hamilton's equations of motion are just differentiate h with respect to p, and that gives you q dot. Differentiate h with respect to q, and that gives you minus p dot. One of the things you see is how parallel q and p come into the equations. Okay, there is a little sign change here, but apart from that sign change, q and p come in an entirely parallel manner into Hamilton's equations. These are Hamilton's equations. Let's apply them to the harmonic oscillator. Let's apply them and see what it tells us about the motion of the harmonic oscillator. Oh, one other thing. Well, okay, let's do it for the harmonic oscillator. How many equations do I now have altogether? How many Lagrangian equations were there? If there are n coordinates, how many Lagrangian equations? N. How many Hamiltonian equations? 2n. Right. The Hamiltonian equations are first order in time, and there are twice as many of them. The Lagrangian equations are second order, and there are half as many of them. So let's take the Hamiltonian for the harmonic oscillator as a prime example. What did I say it was? Omega over 2 times p squared plus q squared. That was it. That's the Hamiltonian. Here it is in terms of p and q. It's a function of p and q. And I can now read off what the equations of motion are. It's really simple. So we start with dh by dp. dh by dp and what is that? That's omega p, right? Omega p. And that's equal to q dot. This is just a statement that the momentum is proportional to the velocity. Not too surprising. Momentum proportional to velocity. Okay, but now let's write the other equation, dh by dq. What is that? That's omega times q. And that's equal to minus p dot. These two are the equations of motion for the harmonic oscillator. Let's just go see how we see that these are equations of motion for the harmonic. They may not look familiar to you, but one step makes them familiar. Take this equation and take its time derivative. What am I getting at? The familiar equations are the second order equations, F equals ma, right? So let's work out the second order equations. Let's get rid of p and see if we can find a second order equation for the coordinate q. To do that, we just differentiate the q equation once with respect to time. That gives us the acceleration, q double dot, is equal to omega times p dot. Just differentiating this one. Good, because now we have p dot down here is minus omega q. So we get q double dot equals minus omega squared q. This, of course, is the standard harmonic oscillator equation of motion for an oscillator with frequency omega. We're not going to solve it right now. Most of you know how to solve it with sines and cosines. And it is just the oscillator. But in this form here, if you look at this form here, and you go back to the circles in phase space, all this is these two equations, the equations for P and Q that tell you what P dot is, or that tells you what Q dot is as a function of P, and what P dot is as a function of Q. It's simply the equation that tells you that things move around on the circle with constant angular velocity, constant, not angular velocity, but constant omega, and that omega is independent of the distance. They all move, all the points on the phase space, wherever you start, the whole thing just rotates around with frequency omega. Wherever you are, for example, if you're over here, you just rotate around with frequency omega. If you're over here, you rotate around with the same frequency. So the whole thing just rotates like a rigid pinwheel. Like a rigid pinwheel. And that's the way a Hamiltonian physicist would think about the motion of the harmonic oscillator. Of course, you can project it onto the q-axis and things just go back and forth. You can also project it onto the p-axis and they go up and down. But thinking simultaneously in terms of P and Q is a very powerful way to think about motion. There's another way you can think about it. Instead of thinking about it as a rigid pinwheel, think about it as the motion of a fluid. Think about it as the motion of the fluid, whole bunches of points filled up with points here. The points represent starting points, represents possible starting points. And think of it as a fluid. The fluid just rotates around the center here with a constant velocity, kind of incompressible fluid, rotating with constant velocity. That's the character of Hamilton's equations. They tell you how points move around in phase space. It's exactly what they do. They tell you wherever you are in Q, the next place that you'll be is determined by how a Hamiltonian depends on P. Whatever the momentum is, the next value of the momentum will be determined by dH by dQ. So that's Hamiltonian mechanics. And I think the next time, I think we'll stop for questions now. I think that's probably enough. The next time we'll get back to this issue of convergence and divergence. What it comes down to, I will tell you right now what it comes down to. What it comes down to is that whether this fictitious fluid has a divergence or a convergence, whether the points in the fluid tend to come together and, what's the right word? Well, it is called convergence, but whether no, it's actually whether the fluid has sources. Sources making it converge or diverge. And what we will prove is that Hamilton's equations ensure that the motion of this fictitious fluid does not have any convergence or divergence in it. But we'll define that carefully next time. And that brings us full circle back to the basic simple ideas that we started with of points moving from one point to another in a deterministic way. Yeah.
The statement you made earlier about systems which, or Lagrangians for which the Q dots could not be resolved as P's being not good systems, is that a provable fact or an empirical?
No, empirical. Well, you could argue that you could prove it from quantum mechanics. Quantum mechanics would go to hell in a handbag if you tried to take some of these other cases. Yeah.
Like a lost on units. You had P squared and Q squared. That doesn't work for me. Omega P doesn't equal Q dot. in terms of units?
How do you know?
Well, P is a velocity and omega is 1 over time. Right?
Yeah, but what's the unit of Q?
Q is a position.
Yeah, no, Q isn't a position. Q is just an abstract coordinate. Okay, good. Let's go back. Good. Let's go back to the basic harmonic oscillator with the usual coordinates and velocities, and then I'll show you how you get to this form. Well, the form that we had before, and we'll try to figure out what the details of the units are. Okay. Do you recognize this? Mx dot squared over 2 minus or plus, depending on whether you're doing energy or Lagrangian, minus k over 2 x squared. Okay. Yeah. Right. Okay. That's it. That's the Lagrangian. We're going to make a change of coordinates. Oh, let's look at the units first of all. X has units of length. Mass has units of mass. Time has units of time. What are the units of the Lagrangian? Energy. Energy. And of course, this does have units of energy. 1/2 mv squared had better have units of energy. Otherwise, we don't know what the hell we're doing. So, right. So this has units of energy, and everything is dimensionally consistent. What is omega? Anybody know what omega is in terms of k and m? Square root of k over m. If you solve the equations of motion, you will find that the frequency of the oscillator is square root of k over m. Okay? All right, so that's what we begin with. Now what I'm going to do is change coordinates. I'll make a change of definition of coordinates. I am going to define a Q so that omega over 2 Q squared, that's this term over here, the potential energy term, is equal to k over 2 x squared. This is the relationship between Q and x. I'm simply forcing it. I'm forcing omega over 2 q squared to be k over 2 x squared. I can do that. I can change variables. And so let's see. So what do I get? First of all, the easy part, we get rid of a factor of 2. And we get rid of omega by putting it in the denominator. But omega is square root of k over m. So what's k over omega? Must be square root of m over k. Yeah. So this is equal to square root of m over k x squared. Yeah. Ah, you're right. It's square root of km. That sounds better. Square root of km. Square root of km. This is the definition of Q. The Q is equal to the fourth root. I don't know how to write fourth root. Yeah. That's the definition of Q, and it ensures that this term over here is equal to this term. But it's at a cost. The cost, it's not really a cost, but nevertheless, Q no longer has units of length. Q now has some cockamamie units that I can't even figure out. What are the units of Q? I don't know. Whatever K was, mass, 1/4 times a length. The units of Q are not the units of length. Okay. Let's keep going and now go to the kinetic term. Let's go to the kinetic term. If Q squared is square root of km x squared, then what is Q dot squared? Well, when you take time derivatives, let's go to, when you take a time derivative of q, the k and the m, those are just fixed constants. They don't change. So it's pretty clear that q dot squared is going to be the same factor, square root of km, times x dot squared. If I take the square root of that, it's just a derivative. No. If q is equal to k over omega, which is square root of km, if I take the square root of this and time differentiate it, it will just become this. All right. So that's q dot squared. Now let's look at q dot squared. Oh, yeah, okay. Let's look at the kinetic energy term over here. What is the kinetic energy term? The kinetic energy term, mx dot squared over 2, that's going to be m over 2, x dot squared. But x dot squared is q dot squared over the square root of km. But the square root of but m over the square root of km is just equal to square root of m over k q dot squared with a 1/2. And what is that? This is just 1 over omega. So all of this becomes 1 over 2 omega q dot squared. Do you remember what I started with for the Lagrangian? It was 1 over 2 omega q dot squared plus q over 2, sorry, but plus q squared times omega over 2. I think that's what we have here. All right. I changed the variables in such a way as to bring it into a certain form. I did it because I knew it was a smart thing to do by the time I got to the Hamiltonian. But the answer to your question is, once you make this change of variables, q no longer has units of length. Q no longer has units of length. That's the only thing that's changed. Q doesn't have units of length. Omega still has units of 1 over time. It's the same omega that it was. Energy still has units of energy. But that's where the discrepancy of units comes from. So, yeah.
P still has the normal units of momentum.
Which does?
P still works out to be the normal units.
P should stay. Yeah, I think so. I think P still comes out to have the same units of momentum. That should be right, I think. No. Depends on which P you mean. The canonical momentum conjugate to Q has different momentum, different units than, yeah.
So if you use x and e,
Mm-hmm. Yeah. Then I would have had to draw ellipses. that, of course, is the reason that yeah, that's exactly right. Yeah. Then I would have gotten, what would I have gotten? All right, what I would have gotten for H would have been not this P and this Q, but the ordinary P and the ordinary X. I would have gotten a different P squared over 2m plus K, K over 2, x squared. So what we would have said is that the energy is a certain coefficient times p squared plus another coefficient times x squared. And as you say, we would have ellipses instead of circles. So that really was the primary reason why I made this change of variables, was to illustrate how symmetric the system really is when the right variables are used.
So I got lost when you said Lagrangian equations are second-order equations, and there are n of them, and then the Hamiltonian equations are first-order equations, and there are 2 of them.
No.
I got lost.
Oh, okay. You didn't understand what I said. Oh, okay. I see. All right. Let's. Okay. Here are 2 first-order equations. First order means only first-time derivatives appear. All right. Here are 2 first-order equations. Combine them together, and you get one second order equation. This is the usual F equals ma. Okay? This is the form that the Euler-Lagrange equations come out in. So two equations, one of which can practically be regarded as the definition of P proportional to velocity, and the other one, just P dot, that is proportional to the force, but you can take these equations, think of them as a pair of first order equations, which are equivalent to a single second order equation.
Okay, now when you did the derivation using Lagrangian formulation,
one second order equation. This is it. That's the Euler, F equals ma, or the Euler-Lagrange equation.
okay, I was thinking of what P and P dot in terms of derivatives of L and Q dot.
Yeah, but just don't even think of P. Forget P altogether and just write L is equal to, you know, what did I say it was? 1 over omega, 1 over 2 omega, Q dot squared plus omega over 2 Q squared. Forget P. Just let's write the Euler-Lagrange equation. dl by dq dot, that's Q dot over omega. And now we have to differentiate it with respect to time. That's equal to dl by dq, which is equal to minus omega q. Okay? This is a second order equation. It's Q double dot over omega is equal to minus omega q. It's the same equation as this one, just multiply by omega. So the Lagrangian equations, if you don't introduce P, and you don't try to get smart and introduce P, the Lagrange equations are second order equations, and there's one of them for each Q. The Hamiltonian equations, 2 for each Q, or 1 for each P and 1 for each Q. But as you see, by the simple trick of differentiating one and putting it into the other, it becomes a second order equation, plus a definition, if you like. Yeah.
When you say that the Hamiltonian formulation is very powerful, is what you're saying, does that somehow amount to saying that that phase space is a better geometrical representation than configuration space?
Different purposes. Different purposes. For example, you see extremely clearly in phase space that the motion has no convergence, and that this fluid, this fictitious fluid, doesn't tend to squeeze together or fly apart, in analogy with the situation for the simple systems that I showed you. That you see very, very clearly. You see cycles, you see conserved quantities being associated with cycles or surfaces in the space. So some things are much easier to see in the Hamiltonian form. Look, each one is what it is and is good for different reasons and different purposes. The real bottom line, and the reason we're doing this, is because the Hamiltonian is a very, very central object in quantum mechanics. Where are we aiming? We're aiming really to get to modern physics. That means we're aiming to get to quantum mechanics and relativity. These are the prerequisites for it. And as we'll eventually find out, the Hamiltonian has a much more intuitive meaning in quantum mechanics than it does in classical. In classical mechanics, this was a bunch of magic, a bunch of fiddling. It's beautiful. You get very, very simple equations. The equations have a simple geometric description, and you can see all sorts of beautiful things. But ultimately, the bottom line is that the real essence of the Hamiltonian comes from quantum mechanics.
So when you write a Lagrangian, it's the kinetic energy minus the potential energy, right? And the potential energy is the integral of the forces?
Yeah.
Can you like motivate? I mean, that's how you motivate that by deriving it backwards, right?
Yeah.
Is there any... Is it always the integral of forces that is function of positions?
I would say it slightly differently. I wouldn't say that the potential, yeah, the potential is the integral of forces if the forces are conservative. But an equally true statement and an equivalent statement is that the forces are the derivatives of the potential. So I think that's a better way to think about it. Forces are derivatives of potential energy. And think of potential energy as being more central than forces. Okay. Yeah.
So I've got one, you were just saying that where we're headed is modern physics.
Yeah.
So you were saying at the beginning of the class that the goal of this sequence is to get us to where we can understand sort of the problems at the frontier.
Hopefully.
So would you say a few words about what some of those are? Like, is it quantum gravity or dark energy?
Absolutely. Quantum gravity, the structure of cosmology, elementary particle physics, the Higgs boson, why it is that neutrinos can't go faster than the speed of light, string theory. The big theoretical problems tend to revolve around the combination of quantum mechanics and gravity, and the implications for cosmology. I say the big theoretical problems. Some of my friends would say, no, the big theoretical problems revolve around elementary particle physics, and both are true. And how all this fits together into some neat structure where all of it is simultaneously accounted for is the big problem. The big problem is what it always was since the day of Einstein, unifying all the various different pieces of physics, but especially cosmology and elementary particle physics, quantum field theory. I actually don't have to tell you that, you know that. And I don't have any great wisdom about what the solution of these problems. Well, I do have great wisdom about. Well, I'm not going to tell you, but. Okay.
I think we'll go home and solve it or something.
Okay. Time to go home.
For more, please visit us at stanford.edu.